So let's get to it. Double angle first. Starting with sine. Sine of 2 theta. That would be known as a double angle. It's an angle theta that's just been doubled. 2 theta. Write this down just to help you recall. Recall from 7.2. What was the sine of alpha plus beta? That's what we learned about last time. Sine of alpha plus beta. What was the identity? What was the pattern? It was sine, cosine, cosine, sine. So it was sine alpha, cosine beta. Now was it plus or minus? Plus cosine alpha, sine beta. Right? That's what we talked about last time. What if we tweaked this formula a little bit to this? Because 2 theta, isn't that just theta plus theta? 2 theta really just means theta plus theta. So what if we now applied this sum formula? What's the pattern when you're adding 2 angles together with sine? It's sine, cosine, cosine, sine, right? But the only difference is it's the exact same angle. So this will be sine theta, cosine theta, plus cosine theta, sine theta. And what does that equal? Aren't these 2 expressions exactly the same? Sine theta, cosine theta, plus cosine theta, sine theta. Because multiplication is commutative. The order of multiplication doesn't matter. So it would just be 2 sine theta, cosine theta. That's the identity. Okay? So we got to keep track of where we went. We started with this, the sine of 2 theta, and we ended up with this. That's the identity. The sine of 2 theta is equal to 2 sine theta, cosine theta. The double angle from cosine is similar to Derive. Cosine of 2 theta. You need to recall what was the cosine of alpha plus beta. I tried to make it kind of like pattern recognition. What was the pattern for cosine if you're taking the sum of 2 angles?
Cosine, 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 sine.
It was cosine, cosine, sine, sine. It was cosine, cosine, and then sine, sine. Now you remember we had to change the plus to a minus as well. That was the other difference. So this would have been cosine alpha, cosine beta, minus sine alpha, sine beta. That's for the sum of 2 angles. And you know, it doesn't matter if the angles are different or the same. We can apply this same sum formula to this double angle. We just have to change 2 theta into cosine of theta plus theta. And now apply the same formula. Cosine of alpha plus beta, let's apply that to cosine of theta plus theta. So it's going to be cosine theta minus sine theta. Now let's clean this up a little bit. How can we simplify that?
Sine squared.
It's cosine squared minus sine squared. There you go. Cosine squared theta minus sine squared theta. And there's the identity. So put a box around where we started and a box around where we ended up. My hope is, in showing you this, that on a test, if you kind of get a little confused on what the actual identity was, you can just quickly derive it, because these aren't that hard to derive on your own. At least these double angle ones. Now, the nice thing, maybe the bad thing about cosine of 2 theta, we can actually change this up a little bit. With sine of 2 theta, it is what it is. 2 sine theta, cosine theta. But this other one, cosine 2 theta, has 2 other forms. I want you guys to think about it for a second. You could probably come up with this. We know some things about a cosine squared or a sine squared, so I'm going to give you a second.
Cosine of theta minus.
I want you to take a second, mess around with these a little bit, and see if you can come up with an alternate form of... There's actually 2 more forms of this that we need to come up with. See if you can use those Pythagorean identities where cosine squared equals something, sine squared equals something. And we need to come up with 2 more forms. What do we come up with? So let me write this over here. 1 minus 2 cosine squared theta. What do we think? It's really, this is really close. There is one that's 1 minus 2 sine squared.
I got -1.
-1?
Yeah.
It should have been 2 cosine squared minus 1 was the other one. 2 cosine squared minus 1. It sounds like you guys had the right idea. What is cosine squared of theta? What could we replace that with?
1 minus sine squared.
Exactly, 1 minus sine squared. So if we take this and change it into 1 minus sine squared theta minus another sine squared of theta, then that changes into 1 minus, how many sine squareds are there? And they're both negative, so it's 1 minus 2 sine squared theta. So there's one version of the same thing. And we can do the same thing with sine squared now. What is sine squared? Sine squared is 1 minus cosine. Actually, we have to do it this way. I'm going to start with cosine squared theta minus 1 minus cosine squared. And here's where you have to be careful. Do these cosines really cancel out?
No.
They don't, because you have to distribute that minus sign. The minus sign distributes there, and it distributes there to make it into a positive cosine. So there's 2 positive cosine squares. So that's 2 cosine squared theta, and then what do we have left? A minus 1. So there's the other form of it. So there's 3 forms of that cosine of 2 theta formula. The most common one is the cosine squared minus sine squared, but the other 2 are very easy to derive from that. All right, tangent. Excuse me, tangent of 2 theta. Also, not too difficult to derive. If you recall, this one's a little bit harder to recall, but it's just as important to be able to recall. What if we had the sum, the tangent of alpha plus beta? This is what we talked about last time. There's still a little bit of a pattern, maybe not as easy to memorize as the sine and the cosine. Tangent alpha plus tangent beta. Let me write this down. Tangent alpha plus tangent beta. There it goes. Over 1 minus tangent alpha tangent beta. So actually, I want you guys to do this. I've derived the other 2 using this method. You can derive the double angle for tangent using the same thing. Apply this formula for when alpha and beta are the same angle. Theta plus theta. See if you can take a second here and derive it. If you think you have something, turn to the person next to you and say, what you got? So tangent of theta plus theta. Applying this formula. Tangent theta plus tangent theta. over 1 minus tangent theta times tangent theta. As I was listening, it sounds like a lot of you have it. If it's tangent theta plus tangent of theta, that's 2 tangent of theta over 1 minus. Now if you're multiplying tangent times tangent, that's tangent squared of theta. So that's the identity. Tangent of 2 theta is equal to that right there. Okay, now that we know these identities, here's how you're going to use them on your homework. Let me show you 2 ways you're going to use these. Here's the first way, just simply evaluating an expression. A lot like what we did last time. Given that the cosine of theta is equal to negative 2/3, and theta is in quadrant 2. Part A what's the cosine of 2 theta? Part B what's the sine of 2 theta? So first of all, let's break this down. What is the cosine of 2 theta in terms of an identity? Not the actual numerical value, but just in terms of an identity. What is the cosine of 2 theta? Cosine squared theta minus sine squared of theta. Do we know cosine? We know cosine. What's the cosine of theta? Negative 2/3. Do we know the sine? We don't. Do we have to use this version of the cosine of 2 theta? Isn't there a version that only involves cosine? Because all we know right now is cosine. What if we changed this into 2 cosine squared of theta minus 1? What if we just use this version? This version only deals with cosine. Right now, that's all we know. 2 times. Now the cosine of theta is negative 2/3, but this is cosine squared, so all we have to do is square that. I moved a little quick there. Let me backtrack. Where did this value come from, negative 2/3? That's given. We know that the cosine is negative 2/3. We're supposed to square that, so it's negative 2/3 squared, and we simply subtract 1 and simplify that. So this is 2 times, when you're squaring a fraction, remember you have to square the numerator and the denominators. It becomes 4/9 minus 1. This turns into 8/9 minus 1. It's negative. It's negative 1/9. So we were able to evaluate this without having to find another trig function. We just used cosine. I don't think we can get away with that for part B, because the sine of 2 theta, what's the identity for that? 2 sine theta cosine of theta. There isn't another version of this. We already know the cosine of theta, it was negative 2/3, but in order to simplify this, we are going to have to figure out what the sine of theta is. So this is what we did last time. We've done actually a lot of this kind of stuff recently. If cosine of theta is equal to negative 2/3, what is the sine of theta? Think about what we did last time. We drew just a random triangle, made it into a right triangle, and figured out the opposite over our hypotenuse, and then we just figured out the adjacent, or whatever side we needed to figure out. We were able to figure it out using Pythagorean's theorem. So with the given information, let's put theta here. Now the cosine is adjacent over hypotenuse, so according to the given information, the hypotenuse has to be 3, the adjacent side is negative 2. We can even call it positive 2, because when you square something, it's going to become positive anyway, so it doesn't really matter. Yeah, so this unfortunately isn't one of those Pythagorean triples. So we're going to have to go through the Pythagorean theorem. A squared plus b squared equals c squared. 2 squared plus the unknown value b squared equals 3 squared. If you take 4 from 9, then b squared equals 5. So b is equal to the square root of 5. The definition of sine then is opposite over hypotenuse, so it's the square root of 5 over 3. But we have to be careful, because here cosine was negative. Does that mean sine is negative, or is this positive? It's in quadrant 2, so we keep it positive, because sine is positive in quadrant 2. So here's the value of sine, which we need. Now all I've got to do is apply it into this identity that we've expanded. 2 sine theta cosine theta becomes 2 times the value of the sine of theta, which is square root of 5 over 3, multiplied by the value of the cosine of theta, which is negative 2/3. This is just basic arithmetic from here on out. Denominator is going to be 9, we know that. What's the numerator? Don't be shy, I know you guys know. This is pretty easy stuff. There you go, negative 4 square roots of 5.
Do you keep it negative or?
Yeah, because theta is in the second quadrant, but if you take theta and multiply it by 2, it's no longer in the second quadrant. Does that make sense?
Yeah.
That's a good question, though. Really good question. Okay, this type of a problem is a little bit different than the identities you've been doing. The identities we've been doing is you have one side and you know exactly what it's supposed to look like on the other side. This one's a little bit different. Here's example 2. Whoop. Is it example 2? Yeah. Write cosine of 3x in terms of cosine of just x. So that doesn't mean that cosine of 3x is going to equal cosine of x. That's not what this is saying. This is saying cosine of 3x is going to equal another expression that only has cosine of x and not cosine of 3x or tangent or anything else. It's only going to have something in terms of cosine of x. It may have other numbers in it, but all we would have to know is cosine of x. One of the reasons for a problem like this, when you get into your calculus course next year, taking the derivative or taking the integral of cosine of 3x is much more difficult than taking the integral or the derivative of cosine of x. So if you're able to manipulate this, it'll make your calculus problems a little bit easier. Now, we don't know an identity for cosine of 3x, but it would logically make sense that we just barely talked about double angle identities. It would make sense we might have to apply that here. Okay. That's actually a great idea. Do you guys agree with this? That these are the same thing? That is true, x plus x plus x. The problem with that is we don't know an identity that deals with the sum of three things. We know an identity that deals with the sum of two things, don't we? This actually isn't the double angle yet. This is the sum formula that we learned about last time, but eventually we're going to have to use this double angle part right here. But how do we expand cosine 2x plus x?
Cosine 2x plus cosine times cosine.
Wait, what's the pattern for cosine? Cosine, cosine. Sine, sine. Cosine, cosine. Okay. So the pattern for cosine is cosine, cosine, sine, sine, with a minus in the middle if we're adding these two angles. So it's cosine 2x cosine of x minus.
We should have done 3 over 2x plus 3 over 2x, because they're the same thing.
We could have done. We could.
That would have made
We
us
could have done
the double angle thing, which is easier.
Is it going to turn into like cosine or like you're going to have to expand the double angle?
Absolutely. Well, we got to finish this identity though. Well, how's it finish? There we go. Sine 2x. Sine x. All right. Step 1 done. This was just that sum formula we talked about last time. Now, you, I'm sure, have noticed we have one of these and we have one of these. Didn't we just learn about those? So we have to expand it again.
We should make those comments.
Why do we have to expand it? Because we want to write this in terms of only. We want to write this in terms of only cosine. Right now we have sines and we have two x's. It only can be cosine of x, not cosine of 2x. No sines either. What can we expand that to? What's the double angle for cosine? There's 3 of them. We want the 2 cosine squared of x minus 1. Sounds interesting. Sounds way more important than what we're doing.
Everything you have
You!
on there. Everything you have on there, I am reading.
So we expanded the cosine of 2x into that particular version. Why not the others? Those others are important. Why do we keep neglecting them? We only want it to be in terms of cosines, no sines. So we chose this version of it. Minus, now what's the expansion for sine of 2 theta? 2 sine x cosine of x. We really couldn't avoid having a sine function there, but you'll see here in a second we can make that disappear pretty easily. We are going to have to distribute here, here, and then what about this?
If you distribute it, you get the sine squared, which you can change out.
Exactly.
You have to expand it and that will make it smaller.
So this becomes 2 cosine cubed of x minus cosine of x minus 2. Keep going, 2
Sine squared of x cosine of x.
sine squared of x cosine of x. Good. Now this might be popping out at you, or hopefully it is. The sine squared of x. That's a problem. We can do something with it. This sine squared of x is 1 minus cosine squared of x. That's this is the Pythagorean identity. Sine squared of x is 1 minus cosine squared of x. So we have that 2 right there, and we have this cosine right here. And over here we had 2 cosine cubed of x minus cosine of x. Whoa! So we have 2 cosine cubed of x minus cosine. Alright, look carefully at this, you guys, that I'm circling. This is kind of unusual, but we have a set of parentheses with terms on either side that need... What do we need to do with both of these terms on either side of the parentheses? We've got to distribute them. The 2 has to distribute, and the cosine has to distribute. So if we can do this, let's say if we can do this all in one glorious step. The 2 distributes, and the cosine distributes to this term. So what does this term right here become? Minus 2 cosine of x. Ooh, good. Now let's do the same thing. Let's distribute the negative 2 to this term as well as the cosine to that term. Positive 2 cosine cubed. Ooh, nice job. All right, let's clean this up. We have a couple of like terms. We have 2 cosine cubed and another 2 cosine cubed, which is 4 cosine cubed of x. And then minus, are these like terms? They are. So it's minus 3 cosine of x. Now consider the expression that we have. Do we only have something in terms of cosine of x? Don't let this fool you. Cosine cubed of x. Yeah, all that really is cosine of x to the 3rd power. So isn't that something in terms of cosine of x? It's just written a little strangely, but cosine cubed of x is really just cosine of x to the 3rd power. So that's still in terms of cosine of x. This is in terms of cosine of x. Everything is in terms of cosine of x. There's no sine. There's no double angles anymore. So that is as far as we need to go.
You know, like,
Yes.
when you, at the first blue equation you have,
Right here?
yeah, when you distributed sine of x into the 2 sine of x cosine of x, what happened when you times the sine of x by the cosine?
This is actually not distributing. Distributing only happens when you have terms separated by plus or minus signs. But these are all multiplying each other. So we actually don't even need these parentheses because multiplication is commutative. I could have taken this and rewritten it in any order. A times B times C is the same as B times C times A, which is the same as A times C times B. Does that make sense? So really what happened here is this changed into 2 sine of x, cosine of x. I just kind of put this in between, and then that changed into sine squared. Does that make sense? So it really wasn't distributing because there was only one term here to begin with, where this is 2 terms, and we had to distribute it to both. Does that answer your question?
Yeah.
Holy moly. You need a break after that one? Yeah. Holy crap. We got to get to these half angle identities. These, I'm just warning, fair warning, these are a little harder to use. But it is what it is. Here they are. Half angle identities. The derivation of these identities is not so simple. So I'm going to not show you them. Let's start with sine. A half angle means you have an angle theta and you divide it in half. That's what a half angle is. So it's the sine of theta over 2. These aren't derived from the double angle or the sum or difference identities. They're actually derived from other identities which we haven't learned. They're called power reducing identities. No. So the sine of theta over 2. It's plus or minus big giant square root 1 minus cosine theta. Where the heck did a cosine of theta come from? Over 2. You got it? The cosine of a half angle, so the cosine of theta over 2.
I think I can see it, dude. I don't understand what the power identities are.
The power reducing?
Power reducing things, but like with the sine squared, you know, with the Pythagorean identities, with the square, and these are the kind of the square root of those. Or at least
I see what you're saying. In a way, yeah. Yeah, in a way you're right. Okay, just take a look at this one for a second. Don't write it down yet.
He's lying.
That is so
That's
fake.
fake. That's
That
not.
is so fake.
No.
Okay, what's the real one? You're really bad liars.
I knew it.
Terrible.
Wouldn't that have been so cool?
You took it too far.
Too far? Where did I start getting it to? The iPie.
The iPod.
Alright, it's a square root.
The 7.
Do it to your next class that you teach this lesson in, and just like,
Technically,
I gotta be more serious.
technically
no,
all the
just
notes.
don't tell them not to write it down, just tell them to write it down.
Tell me to write now, but you guys write in pen.
It's true.
All the notes I've learned, it made me question all the notes I've taken the entire year.
They're all serious. There's the one for cosine. It's almost exactly the same as sine. Just one plus.
So why is the
Cosine.
sine, cosine, and the cosine? Why is it cosine, sine?
I have to go back and show you the
Okay,
power
never mind
reducing
then. Don't
identities.
answer that. Just don't.
Now, tangent of theta over 2 unfortunately has a couple of different versions that are in. It's actually an identity that you might have done in lesson 7.1. I think you did actually. Anyway, it's 1 minus cosine theta over sine theta. That's the identity. However, this has a second version. This could also be written as sine theta over 1 plus cosine of theta. Either one of these, it doesn't matter which one you use, either one of them are the same. I really do think this was one of your exercises on 7.1. You had to prove that this was equal to that. Does this look familiar to anybody or just me?
No, I've seen that.
This one doesn't have square root, no. I swear this was one of your assigned problems.
In our notes or on our homework?
On your homework. Or maybe on notes. We've done this one before. Anyway, maybe I have. I don't know.
In your free time. I think I'll do some free time.
Bored.
I do. I do.
When you get bored, you pull out your math book and just do problems.
I've nowhere to kill.
Read a book or something productive.
Man.
That's productive. You're increasing your.
Let's practice evaluating. Example 4? 3. Example 3. Evaluate. Oh, one thing I need to mention, you guys. Listen for just a second. The sine and the cosine, it is plus or minus square root, which is really two separate expressions. There's a positive square root and a negative square root, but you only use one at a time. You don't use both the positive and the negative. Based on the problem, you have to decide whether you're going to use the positive or whether you're going to use the negative. Does that make sense? You can't just arbitrarily choose. You have to choose wisely. So, with this problem, Not that problem. Different one.
We wouldn't know.
Let's
Pencil
There aren't any good ones. Alright, here's one. Find the sine, the sine of theta over 2 given that the tangent of theta is negative 5/12 and theta is in quadrant 4. Now I want you to write this question down. Well, this actually isn't the question. The question's coming in a second. We know that the sine of theta over 2 is equal to plus or minus big giant square root of pi times I in the sky to the 7th power. No, it's 1. Which one was it? Minus cosine of theta over 2. So here's the question. Do we use the plus or the minus square root? Which one is it? We can't use plus and minus.
Negative.
Let's just leave it up to chance. Does anybody have a coin?
Wait, it's quadrant 4, 2 being positive.
That's really good reasoning. Theta is in quadrant 4, right? The problem is it's theta over 2 that we're doing, not theta itself. Here's what you need to do. Quadrant 4,
So DT's quadrant 4 is not that it's going to be quadrant 2.
if theta is in quadrant 4, that means it's less than 360, but it's greater than what? 270, right? That's where theta is. If theta is in quadrant 4, do you guys agree with that statement? Okay. But we're not dealing with theta, we're dealing with theta over 2, so if we divide everything by 2, then which quadrant is theta over 2 in?
135 to 180.
Yeah, 270 divided in half is 135, and 360 divided in half is 180. So now consider this. Where is theta over 2? It's in the latter half of quadrant 2, but the point is it's still in quadrant 2, right? So in quadrant 2, the sign is positive. So the question is, do we use the positive or do we use the negative?
Negative because of inverse graph. That's how that works.
Theta over 2 is in the second quadrant, and we're taking the sign of it, so it has to be positive. We have to use the positive version of this formula, because theta over 2 is in quadrant 2. You following? So that means we're going to use positive square root of 1 minus cosine squared over 2. But now the other issue is, what the heck is the cosine of theta? We know that, where is it? I lost it.
Triangle?
Triangle, there it is. We know the tangent of theta is negative 5/12. So let's use the information.
Wait, how did you know how to get to use the fucking...
We knew that theta was in quadrant 4. So to be in quadrant 4, that means theta has to be less than 360, but greater than 270.
Right.
But then we had to see where theta over 2 was. So if we divided everything in half, then that became 180, that became 135. So theta over 2 is in this region, 135 to 180.
Oh,
That's in the second quadrant, and the sign is positive in the second quadrant.
Okay.
So let's see, what were we just doing? Right here, tangent, what's the definition of tangent on right triangles? Opposite over adjacent, so this 5, 12, and it really doesn't matter with a negative sign because we're going to be squaring them anyway, so it doesn't make a difference. Yep, this is actually a Pythagorean triple. It's a 5, 12, 13 triangle. So the hypotenuse has to be 13. You can verify that if you want using Pythagorean theorem, but it's a Pythagorean triple. So anyway, what's the sine? No, we don't want the sine. We want cosine. So the cosine is going to be adjacent, which is 12, over hypotenuse, which is 13. Now let's just be careful, though. Theta is in quadrant 4. So it can be positive, because the cosine is positive in quadrant 4. So this changes into square root of 1 minus 12/13 all over 2. And because math is so awesome, we can just leave it like that. No. No, we don't.
Ah, you want to be. Keep tricking us today.
You can just do
Let's go here and then there. You both had good ideas. What was your idea?
12 thirds times 2 over 1.
Yeah, we're going to have to do this over 2 over 1. And you're talking about the reciprocal?
Oh, yeah.
Yeah. Yeah, we're going to have to do that. But we actually need to save that until this becomes one term. We need to change this into one term. Can we do that?
Yeah, you can times 1 by 2 or 13.
Yeah, 1 is just 13/13. So that becomes 1/13. So let's change that. I got to go from here all the way over to here. There we go. So this is the square root of 1/13 over 2 over 1. And that's the same as the square root of 1/13 multiplied by 1/2. And that's the square root of 1 over 26. And then we can stop, right?
No!
No, actually. No.
Please.
This isn't actually, I mean, it's numerically correct. It's just not in its true simplified form. Yeah, I was just going to ask, does anybody know why this is not simplified? And this is why the square root of 126 is the same as the square root of 1 over the square root of 26. And what's the problem with that?
You can't have a square root on the bottom of a fraction for antiquated reasons, which
Don't really matter anymore, but
Over 26.
there you go. This changes into the square root of 26 over 26. Holy smokes. If you want.
Just say yeah.
That's it.
If this is something that can simplify, then you'd have to simplify it. But I don't believe the square root of 26 simplifies. It's 2 and 13, so yeah, that doesn't simplify. If, however, this was the square root of 24, or the square root of 28, then you'd simplify it. But, for mercy's sake, let's stop, for the love of everything holy. That, let me show you something that you ought to, yeah. Where was that?
We went from square root of 1 minus cosine total to 2, and then we got rid of cosine.
Oh, from here to here?
Yeah.
Because we knew the value of the cosine here was 12. Cosine of theta is equal to 12/13. So just replace the cosine of theta with 12/13 because they're the same. Yeah.
Why did the 2 go to opposite side?
If you divide by a fraction, you multiply it by. Is that what you're asking?
I just wonder why the 1
Oh, you just made it a fraction. Yeah.
What would have happened if we used the negative square root of 1 minus?
Then this just would have been negative. It would have been a similar answer, but it would have been negative, which is technically wrong.
So if you ever do the wrong side, how would you know sine versus sine theta?
How would you know to switch it at the end? You know what I mean?
You actually go back and check it.
Well, that's what I was just going to do. So I guess you could and then just check your answer, but
Pick one and then check it until you have to figure out which one it was.
no.
I'm questioning.
So here's what I was going to show you.
Oh, wait, you know what? That might be.
Get your calculators out.
Oh, I see that.
False. Seriously, you guys, the more comfortable you are knowing how to use these calculators, the calculus lab is going to be so much easier.
You're not taking calculus?
You are taking calculus.
Yeah.
So, at no point in this problem did we figure out what theta equals, correct? We didn't really have to know what theta equals. We needed to know where it was, what quadrant it was in, but we didn't actually figure out the exact value of theta. But let's do that now. If the tangent of theta is negative 5/12, then what is theta? The inverse tangent. So inverse tangent of negative 5/12 means that theta is that. Now, is that in the fourth quadrant? Because doesn't it say theta's in the quadrant 4?
Yeah.
That's in the fourth quadrant, right? Are you in radian or degree mode? This is a degree. So this answer makes sense, right? So we're supposed to find out what the sine of theta over 2 is. So I'm going to do sine of that answer divided by 2. The sine of that answer divided by 2. Isn't that what we're supposed to find, the sine of theta over 2? I'm going to hit enter. What happened?
I did the square root of 26 divided by 26. It's not negative.
What did I do? Alrighty. I got it.
See, when you push it to the top, it automatically does.
Oh, jeez. I got to scroll over though. Okay. So what is the square root of 26 over 26 then?
It's the same thing for opposite.
Same thing with
actually.
positive.
It's positive.
You got me on
On a calculator.
What was another version of this angle? The negative 22. Well, the coterminal version, I guess, of the angle. 360 minus. My calculator. There you are. Let's go back.
37.
You want to use a positive angle there.
Just go with use the angles.
Let's go back through the process again.
Theta is in quadrant 4. You just find the angle that's in
The positive angle is in quadrant 4. Let's go through that process again, because it is worth your time. It really is. I know this seems like a lot of work, but on a test with a problem like this that took so long and there's so many ways to make arithmetic errors, it is worth your time to check it. So let's go through the process again. We needed to know what theta actually was, so we did the inverse tangent of 5/12. And that said, okay, theta is negative 22, which technically is in the fourth quadrant, but we wanted to find out what the positive angle measure was, so you just added 360 to that. So that's a positive angle of 337, which is still in quadrant 4, right? But we weren't supposed to do sine of theta. We're supposed to do the sine of theta over 2. So what we did with this is just took that answer, divided it in half, and that's 168.7 roughly. And where is that? That's in second quadrant. So if we take the sine of that angle, 168.7, that's going to be 196 or 0.196. Now if you check the answer that you have, square root 26 divided by 26, those are exactly the same. So just a quick way to check your work. Let's try another one of those. Example, let's call it example 3 still, but part B, because they're pretty much the same thing. So find the cosine of theta over 2 given that the tangent of theta over 7 theta is in quadrant 3. So first of all, if tangent of theta is equal to 24/7, what was the cosine of theta? 7/25. I would have to disagree with that. There we go. I agree with that. It's negative 7/25. Because theta is in quadrant 3, and cosine has to be negative in quadrant 3. So we know what the cosine is.
Yes, Trent was right.
So now, let's use the identity. Cosine of theta over 2 is equal to, at this point it's still plus or minus because we're not quite sure which one's it's going to be. But it's 1 plus cosine theta all over 2. Now let's decide whether to use the plus or the minus. If theta is in quadrant 3, that means theta is less than 270, but it's greater than 180. That's where theta is. But we now need to decide where theta over 2 is. So that's 90. That's less than theta over 2, which is less than... So it's bigger than 90, but less than 135. So where the heck is that? That's the top half, I guess, of the second quadrant. Or the top part of it. Anyway, it's in the second quadrant. Now think carefully, you guys. We're in theta over 2 is in quadrant 2, and we're taking the cosine of theta over 2, which is in the second quadrant. The cosine in the second quadrant is negative. So this is going to be negative square root of 1 plus negative 7/25 over 2. Because remember, cosine is negative 7/25. Yeah, 1 is just 25/25. And if you take 7 from 25, you get 18. So this is 18/25 divided by 2, which is multiplied by 1/2. So this is 18 over 50. This does work out. Awesome. If we simplify, this is 9.
Oh, I just took the bottom one and I was rationalizing.
Oh, did you? Okay. Did you still end up at the same spot?
Yeah.
Okay. So this turns into negative. Well, I don't know. We gotta check this. Maybe we're all wrong.
I checked it.
You checked it?
It works.
I checked it.
Negative 7/6.
We actually. Should we check?
Maybe just 0.6 is negative.
Let's check it. Let's just get into the habit. Let's get into the habit here. Go back to your calculator. The inverse tangent of 24/7 Exactly. You guys, your calculators are right as long as the person using them is clever. This is not incorrect, but it is incorrect in a way. Because where is theta?
Third quadrant.
Quadrant, it's supposed to be quadrant 3, but according to this, that's 73 degrees. That's the reference angle for something that's in quadrant 3. So how do we actually find the angle we need? We add that to 180.
So add 180. Now that gives, divide by 180. What the crap am I doing? All right, inverse tangent of 24/7 equals that plus 180. There we go. Is that in quadrant 3? Okay, now we take that half, or we take that and cut it in half. And that's 126. Now just double check. Is that in quadrant 2, which we thought it should be? That's in quadrant 2. Okay, so now we take the cosine of that, which is negative 0.6. And then check your answer. Negative 3/5 is negative 0.6. So we have happy feelings now because it's right.
Now we have to grab that one.
Not another one of those. Just for the sake of practice, let's end on a high note here.
Let's do 5 plus 6.
Example 4. Verify that the sine of 4x over the sine of x is equal to 4 cosine x cosine 2x. Good old-fashioned identity. Oh, we love these. Are you starting to grow more fond of these as time goes on? Let's decide which is the more complicated of the... Man, I don't know. Whew.
Can we choose the right?
We can choose whatever side. Let's choose the right.
Thank you.
Bad pun, sorry. Well, let's see what happens with the right side. So 4 cosine x cosine 2x. We have to change that into something. We're going to use the identities that we just learned.
Like that we just learned, or?
The ones that we had learned just barely.
How do you tell which one is
You just have to try something and you can't get anywhere and go back and try something else. We have a double angle? Wait a minute. Hold on. I'm just thinking a few steps ahead. There were some identities I didn't cover in this section. One of them in particular was a power reducing identity. And I didn't assign any problems on it. You guys know what powers are, right? Power, like a power of 2, power reducing would take something like this, cosine squared of x, and then you could change it into something that has no power. Does that make sense? That's why it's called power reducing. The thing with this identity, the cosine of 2x, it has 3 versions, but all 3 of the versions have what? Powers. You follow? But if you take a look at where we're going with this, there aren't any powers. So we would eventually have to use a power reducing identity, which we didn't do. So this we're not going to have to do. I thought it would be such a good one too.
I love crossing them out.
Was that? Did I? I don't think so. Not crazier than normal.
Sixth grade, my teacher knew that to be